magic incantations. So unfortunately, decided to go with the old-fashioned mic because problem is the new wireless ones, as soon as somebody puts on their cell phone. So that's see if I can get this somewhat unscrambled. Maybe not so bad. That's borderline.
You leave a word to sit and it just gets itself all knotted up.
Exactly.
Actually gonna.
Try to follow you. So I think since you have the microphone, the questions, you have to repeat the questions so that
Okay.
they get it all out. Okay. Well, welcome everybody, and thanks for coming. Appreciate it. So it's a great pleasure to welcome Matthew Tarr, Professor Tarr, this evening. Thanks for taking time off your lab work. And thanks to your advisors for letting me get time off from your lab work. Anyway, so Professor Tarr is Professor of Chemistry and also Vice President for Research at the University of New Orleans, Louisiana, United States. And we are in the process of trying to work out a joint master's program with New Orleans and the SCSC, so we can resolve the famous M1 problem we have, but it should be a good program. So to go through the usual CV, Professor Tarr did his PhD at Georgia Tech in analytical chemistry. That was after his undergraduate and master's at Emory, Georgia tradition, and then did a PhD at the Environmental Protection Agency in the States. An interesting experience. For him and for me, well, that's a long time ago, so a long, strange trip it's been. But I'll spare you everything in between. But his research interests are mainly in environmental chemistry, some nanomaterials, and in particular photochemistry. And so that's what he's going to talk about in this series. So there are 2 mini courses and a departmental seminar. So this departmental seminar is the professional level, and so I think this is nice, kind of allows me to fill in some of the blanks for, actually not just you, I think most of us here probably need a lot of blanks filled in on photochemistry, so I think it will be a good opportunity, and so these mini courses allow us to bring in some material that we didn't manage to get into the curriculum. I think maybe with UP Lab, I just squeezed light in there once, but probably not much, so I think it will be a worthwhile experience for all of us. So in the tradition of this meeting of the course, it's going to be a chapter talk, so that means we can, that's just the shameless plug for the region, funding it, but now we can get rid of the screen and go back to the appropriate equipment, which is lucky. Now, finding chapters is a challenge these days, but Matt, it's all
Okay.
yours.
All right.
We'll
Thank
get some
you.
Pizza and drinks afterwards.
All right. Good afternoon, everybody. And I appreciate the opportunity to be here and the funding from the region to help with my travel to get here. I've been coming to Lyon for about 5 years, maybe. Started off as just a short visit, and it got a little bit longer. And as was mentioned, we're now working on a joint master's program to allow an M1 at the University of New Orleans, or M1 equivalent, and then the M2 here in Lyon. So I'm going to talk a little bit about photochemistry, and my background is in environmental chemistry. So I'm not going to talk that much on synthetic chemistry. I'm going to talk more about what happens in either environmental systems or in methods that are used to degrade pollutants. I'm not really going to talk too much about those processes today, but I'm going to give more background information on relevant photochemistry, and therefore you won't really see a lot of synthetic chemistry here today. So let's just start off with a very simple question. What is photochemistry? Anybody know what photochemistry is? I kind of I make people talk a little bit. So anybody want to take a stab at that one? Yes? Okay, very good. It's a simple, very simple question with a very simple answer, right? So one of the things that you said is a key point. And that is a photon has to be absorbed. Now that might seem really simple, but you just have to keep that in mind, because a lot of the reactions that happen, it starts to be a little bit less obvious that that's a connection. So just keep that in mind as we go through a lot of these discussions. And to broaden that a little bit more, the reason that photochemistry is effective is because the energy is utilized to overcome the activation barrier. So I'm sure you guys are all familiar with activation energy, and that's the main reason why many chemical reactions don't proceed. So iron, anybody here have you guys might not have cars. Anybody here have a car? I know he has a car. A couple people. Cars rust, right, over time, but they don't just erupt in flames. But it turns out that the reaction between oxygen and iron, or steel, if it's got some other elements in it, is very, very favorable. The reason that that doesn't happen on a daily basis is because it has a high activation barrier, and so the reaction is inhibited. I can give another example. A piece of paper. This is flammable, right? Does anybody see the paper erupting in flame? No, because the reaction is very, very slow. There's a high activation energy, and that's why paper does not spontaneously combust, even though it's a spontaneous and favorable chemical reaction. So this activation barrier is very, very important in preventing many reactions from happening at a perceptible rate. And it turns out that that's where photochemistry becomes important, because by adding energy in the terms of a photon, in the form of a photon, that actually allows you to reach excited states, and that excited state then can help in overcoming that activation barrier. So, again, following on this point that a photon has to be absorbed, let's talk a little bit about photons. And I know many of you have a knowledge of light, but in order to just make sure we cover all the details, I'm going to go over some basics of electromagnetic radiation. So light is a subset of electromagnetic radiation, and a lot of people tend to use the term light when they're talking about photochemistry, but a lot of photochemistry actually happens in the ultraviolet region, and technically ultraviolet is not light. We do hear the term often, ultraviolet light. It's just an improper use of the term. Light is specifically 400 to about 750 nanometers of wavelength, and that's simply defined by what our eyes can perceive. So our eyes have some chemicals in them that absorb photons, and that energy from the photon is then transferred to make a conformational change, which causes a nerve signal, and then we perceive that in our brains as vision. But our eyes are only sensitive in roughly this 400 to 750 nanometer range. Some people could see a little bit shorter wavelengths, and maybe some people could see a little bit longer. Some insects and birds can see below 400 nanometers, but people generally can't. So we define often we put this term visible light as 400 to 750 nanometers. And let's just take a step back and look at a diagram representative of electromagnetic radiation. So electromagnetic radiation is energy in the form of self-propagating electric and magnetic waves. Okay, so that's basically the definition of electromagnetic radiation. You can see the term electromagnetic is right in the name of it. And radiation doesn't necessarily imply waves, but it is waves. This self-propagating, that means it's moving through space, and that's where the term radiation comes. So when light emanates from a source, it radiates out in all directions, and that's where we come up with the term radiation. So if we look at the electric field, so this E now doesn't stand for energy, it stands for the electric field. It can go positive or negative, and if we put this axis as distance, the wave will propagate like that as a sine wave, and it goes from 0 to a maximum, back to 0 to a maximum in the other direction, and back to 0, and so on. That's the electric field. At the same time, you guys might be familiar with the fact that electric fields generate magnetic fields. So anytime you have an electric field, it propagates a magnetic field. So perpendicular, and we can draw another axis here, and we can call this the magnetic axis. We call that B. And it's a little hard to draw this, but I'll just draw this as dotted lines, and I'll put these sort of marks across here to hopefully give the appearance that those are perpendicular. So the electric field is going up and down. The magnetic field would then be coming in and out of the board this way. So the electric and magnetic fields are coincident. So you see when the electric field is 0, the magnetic field is also 0. And as the electric field gets to a maximum, there's a corresponding maximum in the magnetic field. And that's really this self-propagating nature, because the electric field generates a magnetic field, the magnetic field generates an electric field. Okay, and that moves through space. Now there's a few very important properties of electromagnetic radiation. There's the wavelength, which is simply this distance right here from the start of the wave to the maximum, back to 0, to the maximum, to the negative, back to 0. So that's one wave. If you study math, sine waves, that's a full wave. So the wavelength is given the symbol lambda, and this is typically given in units of meters, although people often use nanometers because it's just a more convenient term with the magnitude of electromagnetic radiation. Again, visible light is in this 400 to 750 nanometer range. So that's one important property of light. Another important property is the speed, which in a vacuum is 3 times 10 to the 8 meters per second. You guys are probably familiar with that number. Why light propagates at that speed, I don't know the answer to that question. I'm not sure anybody knows the answer to that question, but there's been lots of demonstrations that this is the fastest that anything can propagate in our universe, and only in a vacuum can you reach that speed. If you go into other media, how many of you run? Anybody here run? A few of you run. Where do you run? In the park here, maybe? Okay. What's around you when you're running? What are you running through? It's this stuff right here. What is this called, all in the room? Air, right? Okay, when you run through the air, do you feel the air pushing against you? A little bit, yes? How many of you have ever tried running in water? Anybody? Everybody here been to the beach before? Yes? And you're running on the beach and you run into the water, what happens? You slow down a lot. Why do you slow down when you get to the water? Because it has more matter, right? The density of water is much, much greater than the density of air. So all those water molecules block you from running. Same thing happens with electromagnetic radiation. It's traveling, and if it's in a vacuum, there's nothing slowing it down. But if it goes into air, there are molecules in the air, and those molecules slow it down a little bit. Not very much in air, because air is not very dense. But when it goes into water, it slows down even more. Glass, it slows down because glass is very dense. And you might be familiar with the term refractive index. That's the relative speed of light in a medium versus in a vacuum. Okay? We're not going to worry too much about those changes. We're just going to leave it as 3 times 10 to the 8 meters per second. The other parameter of one of the other parameters of electromagnetic radiation is the frequency. And this is usually given in hertz or per second, s to the -1. And so this is cycles per second. So again, you have this cycle of going through one wave. So that's one cycle. And however many cycles you have in a second is the frequency. And it turns out that the frequency and the wavelength are connected to each other because the speed is fixed at 3 times 10 to the 8 meters per second, and so it has to propagate at that speed. So if you make the wavelength longer, then the frequency has to go down. So they're inversely proportional. And there's another relationship that's really important, which is this relationship. The energy of a photon is equal to Planck's constant times the frequency. So E here is energy. This is in joules. And H is Planck's constant, which is 6.63 times 10 to the -34 joule seconds. And then frequency, again, is in per second. So if you look at the units, per second times joule seconds gives you joules, and so the units work out. You can also rewrite this like this. E equals hc over lambda, and this is a really important consideration because if you notice, the lambda is on the bottom, the wavelength is on the bottom. So the shorter the wavelength, the higher the energy. And maybe that's something you guys are aware of. This 400 nanometers is higher energy, and this 750 is lower energy. And the reason this is important, one of the reasons it's important, is because of this concept. The photon has to be absorbed to have photochemistry happen, and the reason photochemistry happens is because the energy of the photon allows you to overcome the activation barrier. So just given that piece of information and this piece of information, which of these do you think is more likely to cause a photochemical reaction, 400 nanometer or 750 nanometer? Anybody? There's only 2 choices. The short wavelength, right? Because there's more energy there. Now that relationship is not always true. There are some other factors, but there is a general trend that the shorter the wavelength, the more likely it is for photochemistry to happen, simply because there's more energy and you're more likely to overcome an activation barrier. How many of you have gone in the sun before? Nobody, right? Everybody's been in the sun before. What happens when you go out in the sun too long? You get a sunburn, right? Well, which part of the solar spectrum gives you a sunburn? The red light out here? No. The blue light? No, not even that. You have to go into the UV, which is even more energetic. It's the same thing. You have to get that UV radiation is often called ionizing radiation because it can actually eject an electron because you can overcome the binding energy of the electron in a molecule. And that's why ultraviolet light gives us sunburns. It's photochemistry, shorter wavelength, higher energy, more likely to have a photochemical reaction. There are other factors, but that one is important. So let's just talk a little bit more about the solar spectrum, or sorry, the electromagnetic radiation spectrum. I mentioned visible already, and so roughly 200 to 400 nanometers. This is known as the UV, or the ultraviolet portion of the spectrum. And again, this is a really important region because it's high energy. You can go below this from 10 to 200 is called the vacuum UV. And it's called the vacuum UV because air, oxygen mainly, absorbs in that wavelength region. And so if you want to use these wavelengths, you have to do it in a vacuum. Turns out you can actually do it in an argon atmosphere, but, well, I guess it depends on the wavelength. But typically, we don't utilize this in most either intended reactions or solar-driven reactions because we're usually working in atmospheric conditions, and these wavelengths just don't transmit well. So UV is very important. Again, the visible is about 400 to 750 nanometers. And we'll expand that out a little bit. So you may have seen these letters before: red, orange, yellow, green, blue, indigo, violet. So red light is out here at 750 nanometers. Violet is down here at 400 nanometers. And again, this is increasing energy. And again, that's important in photochemistry because there's a tendency that the shorter the wavelength, the more likely a photochemical reaction is. And then if we go beyond 750, we get out into the infrared and then radio, microwave and radio. And I'm not going to discuss these at all because typically the energy contained in these photons is way too small to drive a chemical reaction. Now that's not always true, but typically photochemistry is going to be in this UV, in this visible region. Now you can, how many of you cook food in a microwave oven? Anybody? Probably everybody, right? Well, that's a chemical reaction, right? Cooking food. If you take an egg and put it in a microwave, it goes from being sort of liquidy to being gelled. That's a denaturing of the protein, so you can think of that as and then precipitation of them. So this is sort of an indirect method. It's not really photochemistry directly. What's happening is these microwaves get absorbed by water, and that causes the water molecules to vibrate, and vibrations are then converted to heat. That's really a form of heat, right? The more motion you have in molecules, the more heat, and that high temperature then causes chemical reactions, can cause chemical reactions to happen. Okay, so that's, we don't really talk about that as photochemistry, but it is electromagnetic radiation-driven chemistry because you add heat, and that heat, again, causes an ability to overcome an activation barrier. So let's just take a couple quick examples over here. With this equation, I'm not actually going to do the math because you guys can do that on your own. I'm just going to tell you the numbers. So if you take 400 nanometer light, which is violet, that equates to 4.97 times 10 to the minus 19 joules per photon. So if you have a single photon of 400 nanometers, it's about 4.97 times 10 to the minus 19 joules. If you go up to 750 nanometers, that equivalent number is 2.65 times 10 to the minus 19, same unit, joules per photon. So the energy, you can see, is declining, and it's nonlinear because this is a C equals lambda nu. It's an inverse relationship. Okay, and if you go to higher or lower wavelengths, obviously you get more or less energy. All right, so let's talk about the sun a little bit. The reason that I like to talk about the sun is because the work that I do is environmental work. And when you go outside in the sun, or just outside in the daytime, you get sunlight coming down. And that actually, if you look out, everybody turn around and look out the back window. What do you see out there? Well, besides that, what do you see all behind us? Trees. What are those trees doing right now? Photochemistry, right? They're absorbing photons, typically in the red That's what makes the leaves green, is that it absorbs the complementary color. And that red light is absorbed, and there's a series of chemical reactions that occur with that energy that's absorbed, and then eventually that energy is utilized to cause a chemical reaction to produce glucose from a series of chemical reactions to produce glucose from carbon dioxide and water. So anytime you're outside, there's photochemistry. Well, I shouldn't say that. If it's daytime, there's photochemistry. Obviously at night, there's not a whole lot of photochemistry. So I'm going to do my best to draw this on the board. I'm not really good at drawing. I brought a little picture for me to be able to, we can zoom in for the people watching. You can look this up on the internet and get this. It's a solar spectrum. But like I said, I'm not really good at drawing, so I'm going to try to copy it as best as I can. So this is wavelength in nanometers, and so I'm not going to draw the whole spectrum. I'm going to go from 250 out to 1250. So remember, this is UV here. Visible is right in this region here, and all this is infrared. So we're really not going to have any photochemistry here, but you do feel this infrared when you go out in the sun, because that will cause heating of your skin. In fact, all of the solar spectrum, when you go outside, you feel the heat on your skin. That's because your skin is absorbing those photons, and that energy is being converted into vibrations and movement of the molecules, and that is also known as heat. So this axis is irradiance, and this unit is in joules per meter squared per nanometer. Hopefully I wrote that right. Okay, and I'm just going to put a number here of about 1.3. because that's the peak. So this is at the surface of the Earth. And this is different than what's in space, because we have the atmosphere between space and the surface of the Earth. And like I mentioned earlier, oxygen absorbs in the UV, and ozone, which is actually part of the chemistry in the atmosphere. There's some photochemistry going on in the atmosphere. There's a lot of ozone up there, and that ozone actually absorbs UV radiation. So we get less UV at the surface of the Earth than there is in space. So this is just the spectrum at the surface of the Earth, and it starts at about 300 nanometers, and it peaks right around 500. It's not really smooth, it's a little jagged. And then right here at 750, there's a big dip because oxygen absorbs at that wavelength. And then when you get up here a little bit below 1,000, there's another dip because water absorbs, and then it kind of goes like that. Okay, so it's not really that accurate out here, but this is roughly what the solar spectrum looks like. And this is extremely important for doing sunlight-driven photochemistry, which is where I do most of my work, because I'm interested in what happens to pollutants when they get out into the environment, typically in aquatic systems. But I'm also interested, or other people are interested in, what happens to what we call natural organic matter. So those same trees out there, their leaves fall off, the leaves die, that material decomposes, and that's what makes the river have its color. A lot of times if you see a brown or black looking river, it's the organic matter from plants that's in the water, and that actually undergoes photochemistry, and it's actually important for a lot of different reasons. What you'll notice though is that there's very little energy down here in the UV. In fact, 400 is maybe here, and so if you look at this region, remember UV is where a lot of photochemistry happens, but most of the solar spectrum is not in the UV region. So there's only a very, very small amount of sunlight that typically is going to be involved in environmental photochemistry. Now the big exception to that is photosynthesis. Obviously plants and other organisms that do photosynthesis have evolved to have chromophores. Chromophore is a species that absorbs light, which are active in the red. So chlorophyll absorbs somewhere out in this region, probably around 700 or 750, where there's a lot of visible light. And that makes sense because the plants need to have that sunlight in order to survive. Okay, so let's move away, a little bit away from the solar spectrum and talk about what wavelengths molecules absorb. And I'm going to actually start off by doing what's called a Jablonski diagram. Anybody ever hear of a Jablonski diagram? Some of you? Okay. So a Jablonski diagram is just an energy level diagram for a molecule. So we start off with the ground state, which is called S1. And the reason it's an S is because it stands for singlet. That just means all the electrons are paired. Most organic molecules are having all paired electrons, and so they're what we call singlets. And then a little bit higher up, we have what we call the first excited state, S2. And then a little bit higher than that, there's, sorry, I got mixed up. Starts at 0 for the ground state, goes to 1, and goes to 2. And you'll notice that the first excited state is relatively far away from the ground state, but the second excited state is not having as big of a gap. That's in the quantum mechanics. If you look at the energy level diagrams, you always have this decreasing energy, and the next excited state is even closer. These are what we call electronic excited states. So remember, molecules have several types of internal energy. They have electronic energy, which is the energy associated with the positions of the electrons relative to the nucleus. You have vibrational energy, which is the energy associated with the nuclei positions and their movement relative to each other. And then you have rotations, which are also quantized, and that's the turning of the molecule in space. Okay, so those are the three types of energy, internal energy, not including nuclear energy, we don't worry about that, of a molecule. We have electronic, vibrational, and rotational. So these are the electronic energy levels, and I should put an arrow here. Energy is increasing in this direction. And then I'm going to write a few of these energy levels here. These are the V0, V1, V2, etc. So these are the vibrational energy levels. And every electronic energy level has associated vibrational energy levels. There are also rotational levels. I'm not going to draw those because it makes the diagram too hard to see. But the vibrational levels are really important because when we have a photon that's absorbed by a molecule, generally, we're going to start off in this S0, V0 state because there's not enough energy at room temperature to have a lot of excited states. And a photon can be absorbed like that. But that's not the only way it can go. It can be absorbed to here, or to here, or to any of the lines that I've drawn up on the board. So we have multiple transitions that are possible from the ground electronic and vibrational state to any of the excited electronic states, including their vibrationally associated levels. Now, the reason I've drawn these arrows here and not here down at the low levels, just between the vibrational energy levels, is because we're talking about electronic transitions, and those overlap with visible and UV energies. These transitions here happen, but those are infrared. So you guys probably have studied infrared spectroscopy, and those are just transitions between these vibrational levels down here. But we're not going to worry about those right now because the energy that we're talking about is UV and visible, and that corresponds to these higher energy transitions. This process of absorbing a photon typically happens on the order of about 10 to the minus 15 seconds. So is that fast or slow? How about really, really, really fast? Okay. There's this principle. I'm not going to talk about it too much. I'll just mention it, called the Frank-Condon principle. Anybody here? That's a quantum mechanical thing. You probably talk about it in organic chemistry reactions. The energy levels of a molecule undergoing a reaction are essentially stationary during this process because it's so fast that the vibration can't happen. Okay? We won't worry about that principle, but it exists. Okay, so you have these excitation steps, and we call this absorbance. So we can draw this over here. We can take a molecule plus a photon, and that gives an excited state molecule. And I'm going to go ahead and add a little 1 here, because remember, these are singlet states. And this excitation occurs between a singlet state in the ground state and an excited singlet state. What that means is the electron that's getting promoted to a higher energy level, it's moving to a different orbital, is not changing its spin state. So you have a plus a half spin and a minus half spin in a paired orbital. One of those electrons is going up to a higher energy level, but its spin is not changing. So they're still paired spin-wise, they're just no longer in the same orbital. So you still essentially have a singlet because all the spins are canceling each other out because they're all opposite. Okay, so that's the process of absorbance. And over here, I'm going to draw a typical, well, an example absorbance spectrum. So we use the term A for absorbance, and we'll put wavelength over here, and I'll just do this sort of the same scale that I had on the other graph, but I won't go quite as far. Because again, typically we're talking about UV and visible. So most organic molecules, and I'm going to differentiate this in a minute, will have absorbance spectra that look maybe something like that, or even like this. And you'll notice, remember 400, that's where visible starts. So lots and lots of organic molecules actually absorb only in the UV. And why is this important? This is important because what's the first rule of photochemistry? First thing I said at the beginning of the talk. And you said it when I asked what is photochemistry. You have to do what before you can have photochemistry? Absorb a photon. Well, here's the solar spectrum, which I'm very interested in. Not all photochemistry people are. And look how much of that spectrum is in the UV. A very, very small percentage of it. But look where most organic molecules absorb, in the UV. So there's not very good overlap between sunlight and photochemistry for organic molecules. Obviously, there are exceptions. All those trees outside, they're all doing photochemistry. But that's a somewhat unique photochemical reaction. Okay, and we'll come back to this concept a little bit later. I did want to talk about a few other processes that can happen here because they're very important. These excited states can go on to react because, again, they have extra energy that overcomes the activation barrier and they can participate in reactions. They can also, let's just call this ionization. You can have photoionization. So the electron, if the energy of the photon is big enough, the electron is completely knocked off, and now you have a radical cation, which is very reactive because electrons like to be paired in molecules. Okay, so those two processes are possible, and I'm just, in general, we're going to have reactions. So I'm going to put a rate constant here, K sub r. So this is the rate constant for a reaction. In addition to that, this excited state and this excited state can relax back down through the vibrational levels, and this is called vibrational relaxation. And that process can actually go all the way back down to the ground state. And usually when that happens, it's called internal conversion. So I use these squiggly lines for non-radiative processes and straight lines for when a photon is absorbed or involved. Okay, so this internal conversion has a rate constant. I'm going to call it KIC for internal conversion. And we also have a process where once the molecule gets down to this S1 V0 state, it can actually release a photon. So you see I've got a straight arrow going down. This is called fluorescence. This is a release of a photon from the excited state molecule. And it has some rules. It only happens from this excited state. But let's just put K sub F there. And then turns out there's another state here called T1. T stands for triplet. A triplet is a molecule that has two electrons that have the same spin. So what has to happen to get from a singlet to a triplet? One of those electrons has to flip its spin. That's a relatively slow process. It's generally called a forbidden process, but it actually can happen. And so this process here of going, in fact, there are vibrational levels here, and that's how it happens. You get a vibrational state in the singlet level that overlaps with the vibrational state in the triplet, and then the electron flips its spin, and you end up with a triplet. That process is called inter-system crossing, ISC. So I'm going to just call that KISC, and I'll spell that out. Inter-system crossing. So you can get to this triplet state, and that triplet state is important for two reasons. One is you can have a radiative process called phosphorescence. So we can have Kp. And the other is this triplet state is able to be involved in certain chemical reactions that the singlet state isn't as likely to be involved in. It has to do with overlap with the other species that it's going to interact with. The reason I'm drawing this diagram, though, is because you'll notice that there's this rate constant for reaction for the excited state. There's this relatively rapid vibrational relaxation. There's inter-system crossing. There's fluorescence. There's internal conversion, and there's phosphorescence. Okay, and there's one more that I'm going to just put up called KQ. That's for quenching. Quenching is when another species collides with the excited state and takes the energy away and brings the molecule down to the ground state. So that has a rate constant associated with it. And just for a frame of reference, this fluorescence is on the order of 10 to the minus 9 to 10 to the minus 5 seconds, just to give you an idea. These processes here, vibrational relaxation, are typically on the order of about 10 to the minus 12 seconds for those to happen. Okay, why is all this important? Of all of these processes, I should put a KR here. So this KR, you add these two KRs together. Of all of these processes, which of them result in chemical reaction? Only one, right? These two pathways. All the other rates are not chemical reactions. So if these are fast, the internal conversion and fluorescence and quenching, what does that mean about the population of these excited states that can undergo reaction? What happens if something decays quickly? It goes away, right? So the concentration becomes low. And I'm sure you guys all know that kinetics is typically concentration dependent. The lower the concentration, the slower the rate. So if these other processes are all very fast, that means photochemistry doesn't have an opportunity to happen. So there's a term that we like to use that's called quantum efficiency. It can be defined more than one way. I'm going to put two definitions up there. It's typically given the Greek letter phi, called quantum efficiency. And one way of defining it is the number of reactions divided by the number of photons absorbed. Remember, to do photochemistry, we have to absorb a photon, but not every photon causes a chemical reaction because a lot of them go to these other pathways. And so the quantum efficiency is just the fraction of those photons that actually cause a chemical reaction. This is typically less than 1 and typically well less than 1. It actually can be greater than 1 under rare circumstances when you have a sort of a feedback loop where energy is recycled back in, but that's not common. Typically, most of the energy is dissipated by any one of these other processes, and very little of the energy goes into chemical reactions. Okay, so a quantum efficiency of maybe 0.1 is very typical for a lot of reactions. The other way of defining this is K sub R divided by K sub Q plus K sub IC plus K ISC plus whatever other case. So the sum of all the other rate constants. So the faster the rate constants are for any of those other processes, the less photochemistry. So that's why a lot of molecules have a low quantum efficiency for photochemistry, because these processes are all very fast, including quenching, which again is collision with another species. Okay, so now maybe you're getting this picture in your mind that we've got limited absorbance in the solar spectrum, in the UV range. We've got limited intensity in that wavelength region, and we've got all these competing processes that make photochemistry relatively unfavorable in many cases. Okay, so now that we've talked about these processes, let's get back to this question: what wavelengths do molecules absorb? I talked a little bit about it already. There's good overlap with these molecular energy level gaps and the UV and visible wavelength regions. So let's just talk a little bit about types of molecules. So if you have alkanes, we're talking about typically single bonds, carbon-carbon and carbon-hydrogen bonds. These types of molecules have very high energy gaps between their ground state and their excited state. So they typically will absorb in the vacuum UV. So these molecules are not going to absorb in the solar spectrum for sure. Alcohols, again, this is typically going to be in the vacuum UV because there's an OH bond now and a CO bond, but typically single bonds have a large energy gap, and that large energy gap means short wavelengths. Now, if you get into carbonyls, well, let's talk about that in a minute. So let's talk about conjugated double bonds. So if you have something like benzene, benzene is typically going to absorb in the around 200 to 270 nanometer region. And the reason for this is when you conjugate, well, I should put in here, isolated double bonds. This is still typically going to be vacuum UV, but in some cases it will overlap a little bit into the UV. So carbonyls, carboxylic acids, for example, typically have a little bit of absorbance into the 200 to 220 or so nanometer range. So you'll notice this trend: single bonds, vacuum UV, double bonds getting towards the UV, conjugated double bonds well into the UV now. The reason for that is when you conjugate double bonds, what happens? You delocalize those electrons, and that brings the excited state down to a lower energy level. Because that delocalization, this is organic chemistry, right? I'm not really an organic chemist. Drop the really. I'm not at all an organic chemist. But when you study organic chemistry, you know that delocalization stabilizes systems. So anytime you stabilize a system, that means you're lowering the energy. So that excited state is also stabilized by the delocalization. And this is one of the important rules for determining, which is the product of a reaction, right? When you stabilize the excited state in a specific conformation, that determines the product. Well, same principle, but now the stabilization causes that energy gap to be lower, and it shifts to longer wavelengths. Now, that's benzene, but let's take anthracene. Oops, see if I can spell it right. You guys know anthracene? I'll draw it up here. I'm not good at drawing these either. Okay, there, I did it. So that's anthracene. So you see, and benzene, I think you guys all know benzene, but I'll draw it up there just for reference. You can see when we go from benzene to anthracene, the conjugation is much more extensive, and therefore the stabilization of that excited state is going to be greater. and that means the gap between the ground state and the excited state gets narrowed. So anthracene typically absorbs in the roughly, well, let's just say up to about 380 nanometers. So you see anthracene's almost up to the visible region because it's much more conjugated. And we could go to tetracene. Tetracene is, you add another ring here, as the name sort of gives away. It has another, I think naphthacene is another name for it, but tetracene is up to about 500 nanometers. So you can see this trend as you get more and more conjugation, you get longer and longer wavelengths of absorbance. And again, this is really important. I just erased the solar spectrum, but now 500 nanometers, that's about the peak of the solar spectrum. Now this tetracene doesn't have a really strong absorbance at 500. Its peak is probably at 400 maybe, but that's still in the visible region. So now you can have visible light photochemistry with this type of a molecule, whereas with benzene, it's all restricted to UV radiation. How many of you know the molecule lycopene? Anybody heard of that one? No? I'll give you a hint, it's red in color. Anybody like tomatoes? Ketchup? Nobody likes tomatoes? I see tomatoes in the store all the time. So somebody likes, a lot of people like tomatoes. The red color in tomatoes is from the chemical called lycopene. And I just wanted to give an example that was a little different because all the other examples I've shown so far for these conjugated systems are all aromatic ring structures, and this one's really hard to draw. So, and like I said, I'm not good at drawing chemical structures. I don't know if I'm going to fit it in. No, I need more space. This is why I'm not, one of the reasons I'm not an organic chemist. Where was I? There. Okay, almost done. Now I just have to put all the double bonds in. Here, 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 here. I think it goes all the way to the end and then it skips one or two. Okay, there. Okay, if I made a mistake, you know, that's okay. You guys can look it up on the internet. This is approximately, hopefully, the structure of a chemical called lycopene. Lycopene is in tomatoes. It's the red color in tomatoes. It's an antioxidant. I don't know if you talk to people who discuss healthy foods and eating a good diet. Fruits and vegetables have a lot of antioxidants. Lycopene is one of them because it's got all these double bonds, and double bonds react really rapidly with free radicals, and then it makes a stable, it's conjugated, so it makes a relatively stable radical from a not stable radical, and that protects other species in your tissue from being oxidized. So lycopene absorbs, it's going to absorb green light. Okay, again, that's in the visible spectrum because look at all those conjugated double bonds. So I just wanted to put that one up there just so you wouldn't get the impression that only aromatic type systems absorb in the visible. There's a range of other types of molecules that will absorb in the visible. A lot of metal complexes will absorb in the visible because there are charge transfer bands between the metal and the ligands. But I'm not going to draw any of those structures up here or talk really about them. Okay, so in addition to these types of molecules, also conjugated carbonyls will typically absorb in the UV and the visible, but again, this conjugation, that's the common theme, right? You got to have these multiple double bonds. And azo compounds. But again, these are typically going to be conjugated okay, so that's the generic structure of an azo compound. But if these R groups are aromatic, these are typically going to be very brightly colored compounds. And you may have heard of azo dyes. They're a relatively common class of dyes, bright oranges, yellows, and reds, I think. Okay? So this is not a comprehensive list of all of the species that absorb in the visible, but it gives you a rough idea that when you're dealing with conjugated double bonds, you're typically going to get absorbance in the UV and the visible region. And again, my interest is this solar photochemistry, and so those are the kinds of compounds that are going to be active in sunlight-driven photochemistry. Okay, so there's a really important concept in environmental photochemistry that I did not mention yet, so we'll start talking about it. Does anybody have questions? You know, you can jump in any time. I know I'm kind of covering a lot of material, but okay? Yes?
Okay, as we studied already, we know that there are up-converting nanomaterials.
Yes.
That convert UV light into, IR or visible light
Yes.
into UV light.
Right.
Are you interested in such applications?
Okay, so the question is generally about upconversion in materials. And I personally don't do work in that area, but there are a lot of people who do. And upconversion, basically what that means is you're typically taking two photons. You can do a lot of two-photon chemistry and energy transfer within those materials. And the reason that can be really important is this issue about spectral properties. If you have visible light at 500 nanometers, it can't be absorbed by a lot of these species. But if you can convert that to 250 nanometer light, it can be. The biggest problem with upconversion that I'm aware of is the efficiencies are pretty low to date. I know there are people who are working on it and doing better, but a lot of times those efficiencies can be quite low. And in fact, I mentioned I didn't call it that, but I mentioned what's called the first law of photochemistry, that you have to absorb a photon to have photochemistry. The second law of photochemistry used to be, I don't remember the wording of it, but it was like had to do with the wavelength. But it turns out that now you can have two-photon chemistry, because if you use laser light, the photon density is so large that you can actually have a 500 nanometer band gap that's bridged by 250 nanometer photons that are simultaneously arriving. All that stuff is being studied extensively, not by me. And the key issue is efficiency, because the likelihood of absorbing one photon is quite low. If you want to absorb two photons at the same time, I think you basically square the likelihood. And so if you have a number that's less than 1 and you square it, it gets even smaller. So the efficiencies of two-photon processes can be quite low. Okay? All right, so let me remind myself. Oh, right. What I want to talk about is something that I didn't mention so far. There are two classifications of photochemical reactions, two broad classifications. There's this type of reaction where you take a starting material, you add a photon, and it causes products to form. There may be another reagent here, but either way, this compound is directly going to products. This process is called direct photolysis, because the species that absorbs the photon is directly involved in being converted to products. The other type of photochemistry is a little bit different, where you go to an excited state, and then this excited state transfers its energy to cause another species to react. So you see here, this species goes directly to products with appropriate reactants. In this process, you get an excited state. That excited state then transfers its energy to another species to go back to its original state. But the other species or subsequent species then react. So this process is called indirect or sensitized photolysis or photochemistry. Okay, so it's a very important distinction between these two processes, and I'm going to talk a little bit more in detail about some of those types of processes. These are really important in a lot of environmental photochemistry, but I think even in synthetic chemistry, indirect photolysis can be really important. So this is kind of like catalysis, right? Because you're starting with a species, and that species doesn't get changed in the process, but it's necessary for the process to occur. Okay, so let's talk a little bit about some examples of some direct and indirect photolysis. So I'm going to go back to using the example of anthracene, and I'm just going to draw it with the circles. I know organic chemists, I think, say that that's not the right way to do it, but it's easier for me. So I'm going to use the example of anthracene, and I'm going to use an S to represent the anthracene. And the reason I'm going to use that S is because it's a sensitizer, the word that I put up on the board earlier. So if you take this molecule and add a photon, remember, anthracene absorbs up to about 380 nanometers. So if I use, say, 300 nanometer light, 350 nanometer light, I can convert this singlet, sorry, the S is also to stand for singlet, to an excited state. Again, that Jablonski diagram that I had up earlier. Now, this singlet excited state can undergo intersystem crossing to make a triplet. It's a lower energy species, but it has important reaction properties. This triplet excited state can react readily with triplet oxygen. So I don't know if you guys remember or learned, oxygen, O2, its ground state is actually a triplet. It has two unpaired electrons, and if you put it in a magnetic field, it's actually attracted to the magnetic field because the two unpaired electrons. So this excited triplet anthracene molecule, or anything similar to that, can interact with triplet oxygen to form this species right here, which is called singlet oxygen, because it's a singlet state. This is an excited energy level of oxygen. And then the sensitizer goes back to its ground singlet state. So this is an energy transfer process. Now, that singlet oxygen can now react with a number of species. Typically, it's going to react with double bonds. So I'm going to, well, let's just generically write it like this. So this singlet oxygen can react with a number of reagents, typically double bond containing species, to form products. Okay, again, the activation barrier is overcome by adding energy in the form of a photon. Triplet oxygen ground state is very slow to react because the activation barrier is high, but once you put this in its excited state, you're much, much closer to that activation barrier, and at room temperature, under thermal conditions, this species will have a substantial rate for reaction with a number of potential compounds to give products. So this is often called singlet oxygen sensitized photochemistry, and this species, anthracene, most of the polycyclic aromatic hydrocarbons, are you guys familiar with the term PAH? It's a common term for these aromatics. These are often singlet oxygen sensitizers. So if you put these kinds of molecules in sunlight, they will produce singlet oxygen. Benzene won't, because benzene doesn't absorb in the solar spectrum, but anthracene will. Does anybody know a common source of these types of molecules, polycyclic aromatic hydrocarbons? Where do we find those in the Earth? Anybody? They're found in oil, petroleum. These are very common molecules in petroleum. So anytime you have petroleum pollution that's in the environment, now these molecules are sensitizing this single oxygen photochemistry. It also can be done in laboratory reactions. And the interesting thing about this is this R here can be the species itself. So this anthracene reacts with singlet oxygen because this has lots of double bonds. And the product, intermediate product of that reaction is the endoperoxide, which I'm not going to know where to put my double bonds. I've got it in my notes somewhere. Oh, it's just here. Well, I probably got some of those bonds in the wrong place, but you get the idea that the aromatic character in this middle ring is broken up by addition of that singlet oxygen to make the endoperoxide. And that can go on to react further. The typical products of this reaction are anthraquinone. I'm just going to draw the circles because it's easier for me. And you can get incomplete oxidation to go to that type of product. Maybe you can read that if I draw it better. Okay, so those are the typical products for anthracene reacting with single oxygen. And this is generically true for any of the PAHs. Any kind of polycyclic aromatic hydrocarbon will react with singlet oxygen. Obviously, the products will differ depending on the structure. So phenanthrene, which instead of having all three rings in a row has a bent structure, the products of phenanthrene reaction are going to be very different than anthracene because the structure of that molecule changes the energies of the different reaction sites. Okay, so again, sensitized photochemistries are really, really important in environmental chemistry, and it can be important in synthetic chemistry as well, because people can use, I mean, if you want to make anthraquinone, I don't know how cheap this is, but this would be a mechanism that you could do to make the quinone. It's probably not that great because it probably has a lot of side products. Another very important class of sensitizers is molecules that will undergo this type of reaction. This is photoionization. And again, these polycyclic aromatic hydrocarbons can undergo this type of process depending on the size of the molecule and the wavelength of the photon. But there's a number of natural organic molecules that are present in river water and seawater that can undergo this type of reaction to give both the radical cation and an electron. And if you're in aqueous media, this then becomes what's called a hydrated electron. And the hydrated electron is a very reactive species, and that can sensitize photochemistry. One of the primary reactions that these hydrated electrons undergo is this reaction to make this species called superoxide. Superoxide is a pretty good reducing agent, but it also can react, it can be protonated to make what's called hydroperoxyl radical. And then if you get two of these hydroperoxyl radicals, they produce hydrogen peroxide and oxygen. And then the hydrogen peroxide, if you have a reducing agent, a hydrated electron or superoxide or any other number, and even an excited state anthracene molecule could potentially undergo this type of reaction. You end up with this species right here, which is called a hydroxyl radical. So all of these species, hydroperoxide, hydroxyl radical, superoxide, hydrated electron, that excited state, even the triplet here, and singlet oxygen, all of these species are called reactive transients. And they're called reactive transients, obviously because they're reactive, and they don't stay around very long because they're reactive. Singlet oxygen in water has around a microsecond lifetime in water. I think it's 2 or 10, I can't remember the exact number. About 2 microseconds is the lifetime of singlet oxygen in water. Its lifetime varies by solvent, but in water it gets quenched. Hydroxyl radical is very, very short-lived. It's, I think, a nanosecond lifetime. Superoxide is a little bit longer lived. So all these species are, again, transient, microsecond or less lifetimes. There are some others that I didn't mention. I'm not going to put them up on the board. You can get, if you're in an aquatic system, if there's carbonate present, you can get carbonate radicals. If there's nitrate present, you can get nitrate radicals. If you've got chlorine, chloride, or bromide, like in a seawater system, you can get like ClO dot is a common reactive transient for reaction with this hydroxyl radical. So there's a wide range of reactive transients that can be formed in aquatic systems in the presence of sunlight and a sensitizer. And remember, this pH is a sensitizer, but natural organic matter, remember I talked about the tree leaves, they fall to the ground, they decompose, they wash out into the river. All of those organic molecules, which are called humic substances, are photosensitizers and produce these triplets, the excited state singlets, singlet oxygen, etc. Okay, so this is the basis of what we call aquatic photochemistry. I did want to mention one other thing about those, but I can't remember what it was, so if it comes back to me, I'll bring it up later. Okay, questions about this part of the discussion? All right, so I think we're getting a little bit close to the time allotted, so I wanted to come back to this issue of quantum efficiency and then a couple other quick closing comments. So I'm going to draw again the solar spectrum. This was irradiance versus wavelength, and I'm just going to make a rough version of it. Okay, remember this is sort of UV that way, visible is sort of here, and IR is up there. And if we look at the absorbance spectrum of an organic molecule, you know, it might look something like that, where it's typically in the UV, maybe a little bit of tailing out into the visible. And the overlap between these two spectra are really important, because the first rule of photochemistry is you have to absorb a photon. So all of this energy out here is completely useless in terms of photochemistry. And that's really important. You mentioned the thing about upconversion. One of the areas where people are very interested in this is not so much photochemistry for degrading pollutants or how things behave in the environment, but capturing energy from the sun and converting it to electricity. So that particular process suffers from this same issue. A lot of the semiconductor materials that are used for photovoltaics don't overlap well with the solar spectrum. So they might absorb up to maybe about here, but you have all this energy from the sun that's not being converted. And so that's a big problem, not really in photochemistry, but it's related in photovoltaics. Okay, so there's another factor, and that's the quantum efficiency, which I talked about earlier. Just because a photon is absorbed at this wavelength doesn't mean that a reaction is going to happen there. So I don't really have a good example. I'm just going to make something up. Quantum efficiency is wavelength dependent. So let's just kind of draw it as somewhat flat out here in the UV, where you're having lots and lots of energy, and that might tail off as you get into the visible, where the photon energy doesn't give an excited state that has enough energy to overcome the activation barrier. This will vary dramatically from molecule to molecule. And like I said, typically this might be around 0.1 or even lower than that. So these quantum efficiencies are very often low. Now, if you want to know the rate of a photochemical reaction in sunlight, you have to combine all three of these. You have to get the solar spectrum, the absorbance, and the quantum efficiency. So it's really the product of all three of these that gives you what's called the action spectrum. The action spectrum is the rate versus wavelength, the rate of reaction versus wavelength. Okay, so all three of these are very important. And if you're not using sunlight, for example, a lot of people do use UV lamps to do their photochemistry, then you still have to worry about the intensity. So the flux of light, so this is photons per second, is going to be a controlling factor. You can think about it as the concentration of light. It's a reagent, right? A photon is a reagent, the chemical is a reagent. And the absorbance is actually, if you remember, hopefully you have learned about this, absorbance is epsilon BC, where epsilon is the molar absorptivity coefficient, B is the path length, and C is the concentration. So absorbance is dependent on the concentration of your chromophore. Your photons is dependent on the concentration is dependent on the photon flux, and then you have to add the quantum efficiency. So all three of those are necessary to determine the overall kinetics of a photochemical reaction. Okay, so let's just, let me see how, okay, we have about 10 more minutes. So let me just talk one more time about types of reactions that are possible with photochemistry, and then we'll wrap it up after that. So I mentioned earlier there's direct photolysis and indirect photolysis. Now I'm going to talk about the types of chemical reactions that can happen to a species. Let's just talk about direct photolysis for now. So the molecule absorbs a photon, it goes to an excited state. That excited state can undergo abstraction type reactions. For example, if you have another species, you can end up with something being taken away from either your excited state molecule. You can have rearrangement. So I know this isn't very descriptive, just call it BA, but you can imagine that the arrangement of those molecules are changing. You can have dissociation, where you're simply just breaking the bond. And by the way, there's two ways that that can happen. You can have homolytic or heterolytic bond cleavage. So the electrons can go one to each side when you break that bond, or they could go all to one and not the other. So we could have A dot and B dot. That would be the homolytic. Or we could have the heterolytic, where both electrons go to the one side. Let's see what else. Substitution, which is going to give us, again, we just take AXY, where we're adding something in, and then we can have addition here. Okay, so these are examples of different types of chemical reactions that can happen when you have photochemistry. This is, again, assuming that this is a direct photolysis, that your excited state is reacting, but you can superimpose on here the other processes, because you can, again, you can have single oxygen or hydroxyradical. Hydroxyradical, by the way, reacts through some of these pathways. Let's just give some examples of hydroxyradical reactions. So it can undergo electron capture, because this is a radical. If it grabs an electron, that makes hydroxide ion, which is much more stable. And so that's a potential reaction. You can have addition to double bonds. Obviously, you have to have a double bond for that to happen. And you can also have hydrogen abstraction. So if you add H dot to OH, HO dot, then you get water as a product. So these are typical reactions that hydroxyradical undergoes. And I've got a few examples, but I don't know if I want to draw them all up. Let's just go to a couple examples with hydroxyradical. because that one's very important in a lot of aquatic photochemistry. You can have, again, a generic, I'm just going to use benzene as an example, but this is relatively generic for most aromatics. You can have electron capture and then subsequent reaction with water and then another hydroxyl radical, and this ends up with hydroxylation. So this is a typical product for aromatics, is you get hydroxylation. That's not the only pathway, because you can also do it by addition. So that hydroxyl radical can add to the double bond, and again, this requires additional reaction. Most of these are 2 electron steps. So you have to have either 2 hydroxyl radicals or some other species. And again, the product turns out is the same, but it just goes through a different mechanism. And then just to give you an idea of a slightly different system, we can do this with a methyl group on toluene, and that reaction can happen here. So that hydroxyl radical can abstract the hydrogen off of the CH3 group, and again, after several steps, you end up hydroxylating on that carbon. So the hydroxyl radical can attack either the aromatic system, or it can attack the alkyl part of a alkylated aromatic. Or in fact, if you just have an alkane, you can also get reaction directly with hydroxyl radical. So hydroxyl radical is very unique because it's such a strong oxidant that it essentially reacts with anything that it bumps into, with the exception of highly oxidized species. So if your carbon tetrachloride, for example, will not react with hydroxyl radical because it's already oxidized. If you get these sort of small di or triacid type molecules, they typically won't react very well because they're very highly oxidized. So typically when hydroxyl radical reacts with alkanes, it's going to be hydrogen abstraction, whereas you can do addition or electron capture with the alkenes or the aromatics. Singlet oxygen, on the other hand, typically only reacts with the double bonds. So singlet oxygen is going to have a much more limited range of reactivity than hydroxyl radical. So hydroxyl radical is very generic. It oxidizes almost anything. Singlet oxygen, on the other hand, is not going to react with as many species. All right, so I think that is, well, we're almost at the end of the time period. So I'll, instead of trying to clumsily draw these other reactions that I'm very bad at drawing, you guys can look things up on the internet. I'll just mention one other type of reaction, even though it's up here. I've talked a lot about oxygenation through hydroxyl radical or singlet oxygen, but especially if you noticed, a lot of the mechanisms that I showed earlier involve free radicals, and even here. So whenever you get free radical chemistry going on, there's a really, really wide range of potential products. And you can have carbon-centered radicals and other carbon-centered radicals that can combine and actually, I don't know if I want to call it polymerization, but you can actually make larger products rather than just making smaller products. You can also get ring opening products here. So even though a lot of these types of reactions are causing breaking of bonds and sort of opening up, you can actually make larger molecules through these. There's an example up here. Oh, addition type reactions. Okay? And whenever you have these free radical type pathways, you can expect multiple products. So it's very, very messy chemistry, not what a typical synthetic organic chemist would want. All right, so I guess we have a couple of minutes, so if there are other questions.
Lots of time for questions.
Yes?
I have just one question concerning you have spoken about the sensitized indices. Is it possible to say that correlation is behind the electron transfer between molecules?
Sorry, say that again.
Is it possible
Oh, collision, yeah.
is behind the electron transfer, between the photosensitizer and the
Okay, so the question is about whether molecular collision is necessary for sensitized photochemical reactions. And I think in general the answer is yes. The one reaction that does not require a collision is actually this hydroxyl radical can actually abstract an electron relatively remotely. So it's like tunneling. You guys know about tunneling. Electrons can jump across space without actually moving through the space because their wave function actually has density relatively far away. I think it's like called a harpoon mechanism. So hydroxyl radical does not actually have to collide to take an electron away. It can get close enough for tunneling to happen. But other than that process, I think, and rearrangement, self-reaction, all the other reactions do require collisions for those processes to happen. Is that what you were asking?
And of course, temperature plays a big role in that.
The what?
Temperature.
Oh, yes. I didn't talk at all about temperature. Well, I did a little bit just to say that typically at room temperature, there's not enough energy for these reactions to happen. So photochemistry, the question, I'm supposed to repeat the question. The question is, what is the effective temperature on these reactions? Photochemistry is often independent of temperature because, remember, I erased it. You've got the overlap between the wavelength of excitation, the absorbance spectrum, and the quantum efficiency. Those three are not temperature dependent in general. But if you have a multi-step reaction, the subsequent reactions will be temperature dependent because those are collisionally dependent. So photochemistry is kind of a little bit weird with kinetics because the direct photolysis reactions are typically not going to be very temperature dependent because it's just the absorbance of a photon in the molecule. For example, where is it? Dissociation. That should not be temperature dependent because the photon is absorbed and the bond breaks, and that's it. But anything that requires a subsequent reaction to transfer abstraction or addition or those types of reactions, there will be a component that is thermally dependent. So the kinetics can be very, very complicated because of that.
To follow up on that question, are there any reactions that you can think of for chemical reactions that are in fact thermal reactions? In other words, if I look at your calculation, about 5 × 10⁻19
Yeah.
joules per photon, if I just to correlate to kilojoules per mole,
Yeah.
that's about 300 kilojoules per mole. So you basically think of heating one molecule to all hell.
Yes.
Right now, how much, there's some, like the singlet oxygen, but it's mechanistic, because 2 requires a singlet species. Does specifically creating radicals. But is there a family of reactions that are essentially thermal reactions, where basically you're just accessing very high vibrational states, essentially very high temperatures,
Right.
effectively
So-
very high temperatures.
So the question is,
process.
are there parallel thermal reactions that essentially can be photo-induced just by adding that activation energy? In general, I think the answer is yes. And in fact, if you look at the rearrangement, I didn't draw a picture, but you can take the azo, I drew an example of an azo, and I put it as a trans, but you can have that cis version. Well, how do you get between? If you think about, in fact, I had an example, I didn't draw it up here, but let's go ahead because this actually answers your question with a real example rather than sort of a generic imagine this or that. Okay, the challenge is, now I have to draw a molecular structure on the board again. Okay, so this molecule this is trans Stilbene. Okay, so you have a double bond, and as I'm pretty sure everybody knows, did I draw that? Yeah, I drew that. Those are on the opposite side, yeah? Okay, so I wrote it I labeled them the wrong way in my notes. Okay, now, I think you guys all know that this has another form. What's the other form of it? It's the cis version, right? And so hopefully I can draw that one. Here, I'll just do the little trick that maybe organic chemists use. It's a lot easier to draw it that way. So there's the cis version of the compound. And how do you get between those two? We all know that double bonds don't rotate because you've got the pi system that is perpendicular to the axis. And if you try to rotate, you've got those p electrons that are overlapping. And if you try to rotate that molecule, you essentially have to break that bond, the second bond in the double bond, in order to rotate. So that's a very high activation barrier. But you can get this to rotate. How can you get it to rotate? One way is to heat it up a lot, right? The other way to do it is to add a photon. And in fact, there are a number of photoisomerization reactions that are well documented. And we actually use this sometimes to measure the amount of light or the amount of other species in our systems by taking a known reaction like this. And then you can just, if you know the quantum efficiency, you just quantitate how much of that is formed, and then you can get the light flux. And by the way, this is a reversible reaction. The wavelengths that these absorb are different, and you can actually get it to go backwards because all you're doing is adding that activation energy. So essentially, you're taking the two of these electrons in the double bond and you're putting them not in a bonding orbital anymore, right? And now you're making a single bond. Then it just relaxes, you know, the bond reforms, and it's just a question of, does it reform while it's still here, or, you know, it's rotating relatively rapidly. So as soon as that double bond reforms, just whichever conformation it's in, that's what sticks. So that's one example of a thermal reaction that can be readily driven by a photon. But I think in general, there are lots of them. Singlet oxygen, in fact, you know, if you look at combustion type reactions, singlet oxygen is a very important intermediate, but normally we don't get that until we heat it up to a relatively high temperature to get the reaction started. But by adding a photon, you can indirectly cause singlet oxygen formation.
But in the reaction with antacene dyne systems, there it's specifically the symmetry. It's a cycloaddition, so
Yeah.
the same species.
All right. Other questions?
I have another one.
Okay, I'm fine.
Just, you know, you took the original example of glucose. That's why, do you distinguish for the chemistry between a reaction in which the light provides the activation energy and one in which the reaction is actually pumping the reaction uphill, right? Because in the glucose synthesis, you're actually doing an endoenergetic reaction.
Yeah.
So
Well,
you're
yes, there's two. The question was, can you differentiate between a kinetic barrier and driving an exothermic or a non-favorable reaction? And yes, you have both. And I sort of didn't mention that. I should have, because I gave the example of photochemistry. Photosynthesis. Photochemistry, the photochemistry that is typically done in environmental chemistry is generally going to be exothermic favorable reactions, because we're typically talking about oxygenation reactions. And it's favorable for oxygen to react with most organic molecules. However, there are a number of reactions that are not favorable that can be driven just like they are in any case. If you want to drive an unfavorable reaction in the unfavorable direction, what do? You add energy. It doesn't necessarily matter if you add that energy in the form of a photon or in the term of heat. Obviously, it depends on the specific reaction, but either method is possible to add that energy that's necessary to drive, or electrically. You can do electrolysis. You can drive reactions in the opposite direction by applying a voltage. So yes, you can do photochemistry. I don't know of a lot of examples besides photosynthesis. I imagine there are some, but in my world of environmental photochemistry, generally we're talking about reactions that are going to be favorable anyway, and we just want to speed them up or provide a pathway. Well, we're speeding them up by providing a pathway that wouldn't be available in the dark.
There's actually, thermally, you can't really drive a reaction. You can drive it closer to a one-to-one mixture, but you cannot drive it in favor. You cannot drive it uphill thermally.
You can,
Photochemically,
yeah, electrochemically you can reverse reactions in many cases. It depends on, some chemicals are theoretically reversible, but there are basically, well, in one case, you have side reactions that can happen. If you heat, often when you heat things up, you get side reactions. And so you get thermal decomposition, whether it's through oxygen reaction or just decomposition of the molecule, pyrolysis type reactions, and you end up making the reaction irreversible simply because those other pathways are easier, either faster or take less energy. And by doing the photochemistry, a lot of times you can circumvent those side reactions simply because you're not creating those pathways. You're only creating the excited state that hopefully you want, and that one then allows you to drive the reaction in a direction that you wouldn't normally be able to.
Okay, well, if there are no more questions, we can have a couple minutes before the judge, but I think we might just go to the other building and then we can chat informally with Dr. Tarr and Alan. So there'll be his departmental conference on Tuesday at 2 p.m. and then another mini course
Yeah.
next Wednesday.
And the next one, I'm going to talk about photocatalysis. So we'll move into the semiconductors and how they, when they absorb photons, how they transfer energy to provide reactions that wouldn't normally happen.
Well, thank you very much, and thank you for coming. And why don't we go over to the other building, the Letterman building, and the reality of 501. Thank you, man.